Good day, I'm Norman Wildberger. We've been talking about multisets and slight innovation called integral multisets last time, and I want to show you how these kinds of ideas fit naturally into elementary number theory, just talking about natural numbers and prime factorization. So that's what we're going to talk about today. So we all know the fundamental theorem of arithmetic, going back to Euclid, absolutely core aspect of the way we think about numbers, which is that every natural number greater than 1 can be written as a product of prime numbers in essentially a unique way. That means that we can change the order of the primes, but otherwise the factorization is unique. So this is certainly a fundamental and foundational theorem. The statement is perhaps not quite as pleasant as one might hope it to be, because we have to talk about this factorization and the non-uniqueness in terms of rearranging the ordering. And it takes a little bit of care to say that in the precise way. We're going to be talking about that in today's video, giving an alternate kind of way of thinking about how to state or frame the result. But I should also tell you that, unfortunately, this theorem is not really true in general. This is a much more serious issue, and we are going to have to talk a lot about this at some future time. Okay, so let me just flag this, that this is a theorem only kind of. Let me give you an alternate kind of way of stating what this theorem might be about. Let's say it this way, that for any natural number n less than or equal to 10 to the 10 cubed, there is an m set P belonging to m set of n of prime numbers such that the actual number n is the product over all the p's in this m set of P. So this symbol pi, this capital pi, means product, sort of analogous to the sigma notation meaning sum. So it means we're taking a product over these kind of indices, and this is an index over a multiset, so we have to include each one of the elements in the multiset as many times as it actually appears in the multiset. And this product of primes P in this m set P, which we could say is P of n. So let me illustrate this, for example. If n is 12, then the multiset P is 2, 2, 3. So it's an m set of prime numbers, and if you take the product of these prime numbers, you get 2 times 2 times 3, which is in fact 12. If n is 726, then this m set is 2, 3, 11, 11. These are the prime factors of this. And some bigger number here. This is 52,387,132. Then it turns out that the corresponding prime m set is 2, 2, 7, 17, 157, and 701. And if n happens to be 41,243, that turns out to be a prime number. So in that case, the m set just consists of that single prime number. So you'll probably be wondering what's going on here with this condition. So I'm saying n less than or equal to 10 to the 10 cubed. So 10 cubed is 1,000. So we're talking about numbers in the Hindu Arabic form whose total number of digits is less than or equal to 1,000, essentially. Okay. So we're restricting our view here to numbers which can be pretty big, a lot bigger than the numbers that we usually work with, but who are definitely bounded. So we're not making a statement about numbers which are bigger than this particular bound. Now there's certainly a lot of scope for changing this. So at first I thought maybe I should just put a 2 here. With a 2 there, so 10 to the 100, I'm certain that this is absolutely true, and we can all verify this, at least with our computers. You take a number with 100 digits or so, your computer can actually factor that into primes. However, if you take a number with 1,000 digits, your computer struggles sometimes to factor it, and it won't be able to factor it if you choose sort of the wrong number or the right number. So computationally, this is already getting to the limits of what our computers can actually do. Now, that's not to say that in 10 years' time our computers can't do a lot more, in which case we might be able to bump this thing up. But you might also say, well, what about theoretically? Well, so it turns out that even theoretically, independent of what our computers can actually do, there is some issue about what happens when numbers get big. And this is going to be an important topic that we're going to have to say a lot more about. We're going to have to talk more about arithmetic with big numbers and the very sort of specific difficulties that start to emerge once you look at bigger and bigger numbers and their arithmetic. So I'm just sort of giving a preview of that kind of dilemma here in this statement. But what we want to concentrate on today is the role of this multiset. This multiset consisting of the primes which figure in the decomposition of the natural number n. So it's really the multiset itself which is somehow the fundamental thing. Every natural number has this associated multiset of primes. And it's maybe not something that you think about if you have a very much of a set theoretic point of view, because it's crucial that we allow multiplicities, because as we all know, the prime factors can occur with multiplicities. Okay? But if we are happy with working with M-sets, then it's very, very natural for us to consider this kind of object as associated to the natural numbers. And this sort of clarifies a number of issues in number theory. It's not a profound, deep kind of observation, but it's a simple observation that allows us to see things perhaps in a pleasant way. Since we're considering this multiset to be rather an important object, let's give it a kind of official name. So let's define P, which is P of n, to be the prime M-set of n. So we'll say that if, considering the number 726, that P of 726 is the prime M-set of 726. And we recall that an M-set like this can be written in a number of different ways. So we could also write it in this kind of form, where we basically determine the various multiplicities of the primes and write it in this additive notation that we can do because we're talking about M-sets. So as the M-set 2 plus the M-set 3 plus 2 times the M-set 11. This form we might call the multiplicity form of the prime M-set. And it very clearly lays out for us what are the primes and what are the various multiplicities that they occur in the factorization of n. Okay, so then there's a natural number theoretical kind of object that one can associate to this. Omega n, this is a relatively standard notation. So omega n is the number of elements in P of n. So it's, in this case, 4. So it's the number of total factors in this prime factorization. And the various primes that occur in P of n have these multiplicities, and sometimes we are interested in the multiplicities, and so we can form a secondary M-set, which we might call M of n, M standing for multiplicities. So where M of n is just recording the multiplicities of the various primes which occur in the prime M-set. So for example, for 726, the prime 2 has multiplicity 1, the prime 3 has multiplicity 1, the prime 11 has multiplicity 2. So M of 726 just records the multiplicities and forgets about the actual primes themselves. So it sort of loses information, but it's a simpler kind of object. And then W of n can be defined to be the size of Mn, which in this case would be 3. So that's counting the number of distinct prime factors of the natural number n. So here are some fundamental natural number sort of functions associated to these perhaps even more fundamental data structures associated to the natural number n. The prime M-set of n, and this a secondary sort of multiplicity M-set of n. And now we have a very natural and important sort of fact that for any natural numbers n and m, The prime m set of the product n times n is the sum of the prime m set of n with the prime m set of m. And this is sum in the sense of m set addition, where we just take the two m sets and dump them together to form a bigger m set. So for example, P of 12 is the m set 2, 2, 3. P of 7, 2, 6 we've seen as the m set 2, 3, 11, 11. So if we multiply these two numbers together, we get 8,712. And its prime m set is just the sum of these two, which is just what you get when you put them all together. So 2, 2, 2, 3, 3, 11, 11. So all the multiplicities of various primes simply add. That's kind of obvious, right? So at the level of these prime m sets, multiplication, which is usually the more complicated sort of basic operation, has a very simple form. In terms of multiplication, you're just adding the corresponding prime m sets. All the difficulty from the point of view of prime m sets rests essentially in the other operation, that of addition. Okay? So how do you find the prime m set of n plus m if you know the prime m set of n and the prime m set of m? Well, this is a very, very profound kind of number theoretical question about which we know essentially nothing. There's nothing sort of non-trivial, really, that I think we know. It's almost fair to say. So if you could make any kind of significant statement about how to find this in terms of those, you would become famous very quickly. But nevertheless, abstractly, we could still sort of introduce a kind of operation on these prime m sets to correspond to the addition of the corresponding natural numbers. So we could define P of n, so circle sum P of m, in this context, to mean the prime m set of the sum of n and m. Okay, but just because you know the prime factorization of one number and you know the prime factorization of another number, how are you going to find the prime factorization of their sum? And pretty well the only thing you can do is you can calculate their sum and then work hard to find its prime factorization. Doesn't seem to be any more direct way of doing that. I'd like to briefly mention just a few standard number theoretical functions which play a very important role in the theory. Tau of n and mu of n. So tau of n is the number of divisors of n, and that can be stated relatively simply in terms of the m set m of n as the product over m in m of n of m plus 1. So for example, tau of 726 is the product of the m plus 1s as m ranges over 1, 1, 2. That's the multiplicity m set of 726. And so we have to multiply 2 times 2 times 3, which is a total of 12. So telling us that tau of this, the number of divisors of this thing from 1 up to itself is 12. And so, for example, tau 105 is the product of 3, 5, and 7, so its multiplicity m set is just 1, 1, 1. And tau of that will be the product of 2 times 2 times 2, which is 8. Another famous number theoretic function is the Mobius function, usually denoted mu of n, which is a little bit more complicated to write down, but one way of saying what it is with this formula, that if the number of elements or if the size of mn happens to equal the size of Pn, then the Mobius function is minus 1 to this common size. And otherwise it's 0. What this is saying, if you think about it, is that these two things will be equal when the number has prime factors which are all appearing with multiplicity 1. So there are no repeated prime factors. If the number n has that property, then the mu of n is minus 1 to that number. So if it has an odd number of prime factors, it's minus 1. And if an even number of prime factors, it's equal to plus 1. So mu of 726, this had a total of well, there were 3 in this set and 4 in this set, so they were not equal. So mu of 726 would be 0. But mu of 105, that has 3 distinct prime factors, 3, 5, and 7, and so mu of that is -1 cubed, which is -1. Okay, so we can see that there's some elementary number theoretical functions which very closely linked to these M sets, P of n and M of n. It's worth pointing out in this story that there's also a role for the concept of a list here. And that's because the prime numbers themselves are naturally ordered by size. So there's the first prime, 2, and then 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and so on. So we can talk about the first prime, the third prime, the seventh prime, and so on. So what we can do now to a natural number n is associate what we might call the prime list, L, or L of n, which is the list of multiplicities in the prime M set P of n. So P of n records the various primes that occur in the factorization of n. So if n is 12, then we saw that P of 12 was the M set 2, 2, 3. So we can make a list out of that by saying, okay, well, in terms of this list, the first prime occurs twice. The second prime occurs once. So we can make the list 2, 1, giving us the multiplicities of the primes in their correct order. So for example, for 726, we saw that the prime M set was 2, 3, 11, 11. And so we can associate to that the list 1, 1, 0, 0, 2. Just the various multiplicities of the primes that occur using this standard ordering of the primes. 175, 0, 0, 2, 1, because there's 2 5s and 1 7. And 31, well, that's a prime. And a little bit further on in the list, so we have to have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then finally a 1. So practically speaking, you can see this is going to be more useful if the number is relatively small and all the prime factors are very small. If we're talking about very big numbers, they typically have very big primes, and then these lists are going to be very long. But nevertheless, sort of theoretically, this is another useful tool for us to think about as a way of representing or understanding or sort of capturing this all-important prime factorization of a natural number. Now I want to extend our discussion a little bit and consider fractions and corresponding integral M sets. So integral M sets are these more general kinds of data structures. They're like M sets or M multisets, but elements can occur with negative multiplicity as well as positive zero multiplicities. And we're going to see that this naturally fits in this discussion when we try to sort of extend thinking about prime factorizations of natural numbers to prime factorizations for fractions. So a fraction, I remind you, was an expression of the form m over n, where m and n are natural numbers. So we're just thinking about like positive rational numbers now, okay, things which are greater than 0. So the fundamental theorem of arithmetic naturally extends to fractions, and it therefore naturally leads us to consider integral M sets. So for example, if we have 5,123 over 135, then the numerator has a factorization, which is in this case is 47 times 109, and the denominator has a factorization, which is 3 cubed times 5. Now in this case, this fraction was already in reduced form. It didn't have any common factors in the numerator and denominator. That could also happen, of course, in which case we would then sort of remove those common factors before we went to the next step. The next step is to recognize that we have here really the makings of an integral M set, because the numerator, which is an ordinary natural number, has a prime M set, just as we were talking about, namely 47 and 109. And the denominator, of course, also has a prime M set, but it's natural to put these together into an integral M set for the fraction itself. And what happens there is that the prime factors of the numerator occur with positive multiplicity, and the prime factors of the denominator occur with negative multiplicities. So that 3 cubed is represented by a 3 occurring there with multiplicity minus 3, and there's also a 5 occurring negatively. So a more complicated example, here's some bigger fraction, here's a prime factorization for it, and then the corresponding prime integral m set would be the m set, the integral m set, where you put the factors of the numerator there with positive multiplicity, in other words in the regular kind of fashion, but the denominator's factors figure with negative multiplicities. This is a very natural thing to do. Okay? And it sort of reveals that this integral m set notion is really not so strange as you might think. Okay? It's really a justification for why it's a useful concept, because it's exactly encoding what we wanted to encode, namely the factorization of these fractions. So it naturally gives us an extension of the fundamental theorem of arithmetic from natural numbers to fractions, which is clearly a useful thing. So we've expanded our view here to think about these prime m sets also for fractions. So this fundamental result that we saw for natural numbers now extends to fractions, but in addition we get a second kind of formula that covers division as well. So the advantage in going to fractions is that we can introduce this new operation of division. So for any fractions R and S, the prime integral m set of the product RS is the sum of the individual prime integral m sets, while now the prime integral m set of the quotient R over S will be the difference of P of R minus P of S. And so here's just an illustration to show you that. Here's a number R and S. Here are corresponding factorizations. Here are the corresponding integral m sets, or prime integral m sets. So there's 2 cubed represented by those 2's in the numerator, and also 5 squared represented by those 2 5's. And in the denominator there's a 3, a 7, and 19. They're all appearing with negative multiplicities here because they're in the denominator. And similarly here we have a 2, a 7, a 13, and then a 3, and a 5 with negative multiplicities. When we take the quotient, R over S, well, we're going to get this thing here. And then multiplying essentially by the reciprocal of the second one. That's how you take the quotient. We're going to get a 2 squared, a 3 altogether, because there'll be a 3 squared coming on top there and canceling with that 3. There'll be 5 cubed all together in terms of 5's, and the denominator we have, the 3's are gone. There's a 7 here. The 7 will be augmented by the 7 here, so we're giving a 7 squared. And then there's a 13 and a 19 here. And so the prime integral m set of the quotient has a 2, a 2, a 3, 3 5's, and then in the negative part of it, a 7, a 7, a 13, and a 19. And hopefully we can see that this is indeed what you get when you take this integral m set and you subtract this integral m set. Remember that you can do that just by doing basically each element's multiplicity separately. So the number of 2's here is 3, the number of 2's here is 1, the difference is 2. So when we take this thing minus this thing, we get 2 occurring twice. And same thing with all the other elements. So this just illustrates that this idea of an integral m set is pretty natural in this context of working with the arithmetic of fractions. So I want to finish by sort of observing that when we're doing arithmetic with these fractions in the context of these integral m sets, that multiplication and division is very simple. We're just working with the sums and differences of these m sets. Addition and corresponding subtraction is of course much harder. But I want to point out that the difficulty of addition in this setting is not really appreciably more than the difficulty of addition with just regular natural numbers. Okay, so usually addition with fractions is, for most students, considerably more challenging than addition with natural numbers. Because you have to remember this formula: A over B plus C over D equals A times D plus B times C over B times D, I suppose. Right. So Let's illustrate this with an example. Suppose we have two fractions, n and m, and this one is 117 over 50, and here's its prime integral m set. And the second one is 35 over 44. The factor is 5 times 7 in the numerator and 2 times 2 times 11 in the denominator. Okay, so we've seen that the product is just obtained by taking the sum. So you just take the sum respecting the multiplicities and you get that for the prime integral m set. And the quotient, again, is just obtained by taking the differences of the two prime m sets. Now let's consider more interestingly the sum of these two fractions. Okay, so we are using this sort of circle sum addition to represent how addition looks like at the level of these m sets. Okay, so let's have a look at what actually happens here. So I'm going to rewrite this p of n and this p of m here in a slightly non-standard way. What I'm going to do, first of all, I'm going to put all the negative multiplicity objects in the second row and all the positive ones in the top row. It makes it a little bit easier to read and sort of corresponds more clearly to the fraction. That's just a notational convenience for us. It doesn't actually have any meaning as far as the m set itself goes. But notice that what I've done here is I've rewritten things, but I've changed it a little bit. So here we just had a 255 in the denominator before, a -2, a -5, and -5. Now I also have a -2 and a -11. And to compensate for that, I've introduced a 2 and 11 up here, so that that positive 2 and that -2, these are just multiplicities of 2, essentially cancel out. And similarly, this 11 and this -11 in terms of multiplicity essentially cancel out. The reason I've done that is because I'm essentially cooking up the m set equivalent of common denominators. I've looked at the negative occurrences there and the negative occurrences here and then figured out which is the, well, basically the union of those. Here the negative entry is 2, 2, 5, 5, and 11. So that covers both this one and this one. And I've repeated things over here. Now in order for this to equal this, I've also had to introduce some more fellows in the numerator, because going from here to here, I've added a 5 and a 5 with multiplicity -1 down there. And so I have to add a 5 and a 5 with +1 multiplicity up there. So let me make the remark that, so with integral m sets, there is now this possibility of having more than one way of writing down an m set. It's not just multiplicity positive, because we have multiplicity positive or multiplicity negative, and if we have a +1 multiplicity and a -1 multiplicity, that sort of amounts to a 0 multiplicity. So technically speaking, we could allow ourselves to do this, and it's a convenient kind of thing to do in this case, because now if we think about adding the corresponding fractions, this corresponds exactly to the usual formula for adding fractions. In other words, we can sort of peel off this common negative part, namely -2, -2, -5, -5, -11, and then peel off the positive parts, which are 3, 3, 13, 2, 11, and 5, 7, 5, 5. So what we have to do here is we have to take the sum, this circle sum. In other words, we basically have to compute this natural number, we have to compute this natural number, we have to take the regular sum of those two natural numbers, and then we have to factor them. And then we take the regular m set sum with this negative part. So you can think about that, but the point that I'm trying to make here is that at the level of these integral m sets, the arithmetic with fractions is necessarily complicated because there's this circle sum kind of operation, which is very, very hard to do. But that it's not really appreciably more difficult than just circle summing ordinary natural numbers, which corresponds to the fact that when you add fractions, you do have to add natural numbers up in the numerator. Okay, so some addition has to be done, but that's essentially as much as there is. So that's just a small observation that I put out there for your amusement. Okay, so we've been talking about multisets and that they are quite interesting objects, that they form a very legitimate, a powerful tool in many different situations. And we are going to see a lot more applications of M-sets further on. But I think the next thing that we have to do is go back to our 4 basic kinds of data structures: lists, order sets, M-sets, and sets, and now cover the last one in our list, which we still haven't actually gotten around to, talking about sets. Okay? So sets are, of course, also very important kinds of data structures, but they should be thought of as being one of these 4 different types. Not necessarily better, not necessarily worse, just one of 4. That's what we're going to do in our next video. Have a look at sets. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.